Dark matter is a hypothetical form of matter that is thought to make up approximately 85% of the total matter in the universe, and is invisible to telescopes. Despite its name, dark matter does not emit, absorb, or reflect any electromagnetic radiation, making it invisible to telescopes. However, its existence and properties can be inferred from its gravitational effects on visible matter, radiation, and the large-scale structure of the universe. The existence of dark matter was first proposed in the 1930s by Swiss astronomer Fritz Zwicky, who observed that the mass of galaxy clusters was not sufficient to account for the gravitational forces holding them together. Subsequent observations of galaxy rotation curves, gravitational lensing, and the cosmic microwave background have provided further evidence for the existence of dark matter. One of the main lines of evidence for dark matter comes from the observed flat rotation curves of galaxies. Rotation curves are a plot of the rotational velocity of stars and gas in a galaxy as a function of distance from the center of the galaxy. According to Newton's laws of motion, the rotational velocity of stars and gas in a galaxy should decrease with distance from the center, but this is not what is observed. Instead, the rotational velocity of the outer stars is observed to be constant, suggesting that there is a significant amount of additional matter in the galaxy, beyond what can be observed, providing the extra gravitational force needed to keep the outer stars rotating at a constant velocity. Another line of evidence for dark matter comes from gravitational lensing. This is the phenomenon by which the gravity of a massive object bends and magnifies the light from a background object. By studying the distortion of background galaxies caused by the gravity of foreground galaxy clusters, scientists can infer the distribution of matter in the foreground cluster. These studies have revealed that there is a significant amount of additional matter in galaxy clusters, beyond what can be observed in the form of stars and gas. The cosmic microwave background, CMB, also provides a strong evidence for dark matter. The CMB is the faint afterglow of the Big Bang, and is observed to be almost perfectly uniform, with temperature fluctuations of only a few parts in 100,000. However, the observed large-scale structure of the universe, such as galaxy clusters and large voids, could not have formed solely through the gravitational pull of the visible matter. The observed structure of the universe is consistent with the presence of dark matter, which would have provided the additional gravitational force needed for structure to form. While the existence of dark matter is widely accepted, its properties are still not well understood. The leading candidate for the nature of dark matter is a new type of particle called the weakly interacting massive particle, WIMP. WIMPs are hypothetical particles that interact only very weakly with ordinary matter and radiation, which would make them difficult to detect directly. Many experiments are currently underway to search for WIMPs, such as the Large Hadron Collider, LHC, at CERN, and underground detectors such as LUX and Xenon. Another possible explanation for dark matter is it could be composed of primordial black holes, formed in the early universe. But this explanation too is not completely understood, and the detection of them still ongoing. Despite the evidence for its existence and the many ongoing experiments designed to detect it, dark matter remains one of the greatest mysteries in physics and astronomy. Understanding the nature of dark matter is one of the most important problems in cosmology and particle physics, and its solution could have far-reaching implications for our understanding of the universe. In conclusion, dark matter is a mysterious and intriguing subject that scientists are still trying to fully understand. While its existence is well established, its properties and nature remain a mystery.